Okay? So if we have du equals TDS minus PdV, all right? U is a function of S and V. And we note that U is a state function. And we remember from what seems like a lifetime ago, it has an exact differential expression. Okay? That means I can write the total differential of du as the following. And I'm going to ignore all this other crap that I've written on the slide, and we're just going to note, okay, we see u is a function of s and v. We impose it as an exact differential, which will go as follows. Partial of u with respect to s at constant v ds. Now the other relationship, partial of u by the partial of v at constant s dv. Okay? And now this is powerful because we have here this fundamental equation. Let me write that right underneath. Du is t ds negative minus p dv. Why is this so powerful? Why am I excited about it? Why am I making such a big deal? Because this is going to give us the thermodynamic definitions of temperature and pressure themselves. Check this out. The partial of u by the partial of s at constant v equals temperature. And in fact, saying, looking at how u changes with entropy at constant volume, so the partial of u with respect to the partial of s at constant v is a better indicator of temperature than temperature itself. In fact, it is temperature. So we've talked about how temperature is really just, it's a human construct. It's a thing that I can measure, okay? How hot is it outside today? What's the temperature, okay? What that really means, the bigger picture for the universe, is this. That's really what temperature is. Super cool, okay? Well, what about pressure? And we know that there's a negative sign in there, and that's okay, okay? But the partial of u with respect to volume at constant entropy, negative, is pressure. And we remembered, hopefully we remembered, back from our Joule-Thomson discussion, that the units of u divided by v give us pressure, okay? So that's really, really cool, okay? And so what else is going on? So what else can I say from this, all right? Well, we remember that because du has an exact differential expression, okay, I can say the following. So I'll remind you of the math. df equals g dx plus h dy. And this is a reminder of all those exact derivatives we did. So now if I take the partial of g with respect to y at constant x, that's going to equal the partial of h with respect to x at constant y. And I didn't put this in before, but we also recognize, because this is already a differential, these two are actually going to give us the second derivative of f with respect to x and y. Okay? So why is all of that a big deal? Well, now let's play with this fundamental equation. Okay? And let's do exactly what I just did. So now, partial of t with respect to v. So remember, just like I did here, I said g with respect to y. So now let's do t with respect to v at constant s. Okay? Equals. So now we've got h with respect to x at constant y. So that's going to go equals, and then I've got a negative sign there. Negative partial of P, okay, with respect to S. I'm putting this together in the exact same way here. And now that's all at constant V. And now following the same way I put this together, all of that's going to equal the second derivative of U with respect to S, with respect to V. But bam, if I had a mic, I would drop it. If back in the day when we were in the classroom, I used to do the LeBron James. I take the chalk, throw the chalk everywhere. I'm the LeBron James of the chalkboard. Why am I so excited? This is a freaking Maxwell relation. Holy shit, right? Do I have an extra piece of paper? Let's keep going here. Let me put an extra piece of paper here, okay? Right? V, A, T, U, G, S, H, P, arrow this way, arrow this way. So we were just playing with U. Okay, U is sandwiched between S and V, which equals derivatives at constant S and derivatives at constant V. The derivative at constant S goes partial of T, right? Travel the arrow. Partial of T by the partial of V at constant S. The derivative in V, now I'm going against the arrow, so negative sign. Partial of P by partial of S at constant V. That's the same thing we just came up with. This is awesome. If you don't think it's awesome, that's okay. You don't have to do physical chemistry in your life. But I think it's awesome. I think this is totally cool. This is where these relationships come from, okay? So let's keep going with this, okay? And so there's a bunch of proofs we can do. Like I didn't do this before. Let's see what I have coming up next. Yeah, okay. So we talked about this whole internal energy thing, or excuse me, internal pressure. So we talked about this earlier, that the partial of U with respect to V at constant T is this internal pressure, which we said is 0 for an ideal gas, and we said is A times N over V all squared for a van der Waals gas. Where does that come from? Well, it actually comes from the Maxwell relations. I'm not going to finish through this, okay? But if we were to go through, starting with partial of U equals, right, the partial of U by the partial of S at constant V ds plus the partial of U by the partial of V at constant S dV. If we were to start here, okay, it can be shown. I'm just going to like kind of show you, hint, hint, wink, wink, how you start this derivation. Pi t from the Maxwell relations, you can put this all together. That this all equals a partial of P by the partial of T at constant V minus P. And then from there, this leads you to A times N over V squared. So we can use these Maxwell relations to come up with other relationships that we maybe didn't know existed before. So they really are a cipher or a code for the universe. That's how I really like to think of these Maxwell relations. They give us the key to physical observables of the universe. I'm going to show you some even bigger ones here. I'm going to skip. I think I gave myself